Hello viewers, in today's class we are going to discuss yet another important application of Lagrange's mean value theorem, right? So here once again we'll prove an important inequality using the famous Lagrange's mean value theorem, right? So here we have this inequality that is using Lagrange's mean value theorem. We have to prove that log of 1 plus x is greater than x minus x square for all x greater than 0, right? So here instead of log log, we can also write it as ln 1 plus x greater than x minus x square, right? So here we'll prefer this notation. So let us start, and before moving further, let us quickly see the statement of Lagrange's mean value theorem, right? So Lagrange's mean value theorem says that if we have a function y is equal to f of x, which is defined in some domain D, and if we take a interval that is a comma b, which is a subset of this domain D, and if f of x is a continuous function in the interval a comma b, and if this function f of x is also differentiable function in the interval a comma b. Here we have the open interval and here we have the closed interval, right? So if this function satisfies these two conditions, that is f of x is continuous function in this interval and f of x is derivable or differentiable in this interval, then the mean value theorem says that there must exist some number, say alpha, such that alpha lies between a and b, such that f prime of alpha is equal to f of b minus f of a divided by b minus a, right? So this is the statement of Lagrange's mean value theorem, right? So here we'll utilize this statement to arrive at this inequality, right? So now here let us first take an appropriate function here, right? So what we will do, we'll assume that we have a function, say y is equal to f of x, that is equal to a log of 1 plus x minus x, and which is defined for all values of x greater than 0, right? So the first thing is to assume a function f of x which is equal to log of 1 plus x minus x, right? Now let us apply the conditions of mean value theorem to this function, and we can easily see that this function f of x is a continuous function and differentiable function for all x greater than 0, right? See, a log function is a differentiable function in its domain, right? And x is the polynomial function, right? So f of x is a combination of two functions, right? Two continuous functions. So log function is continuous and the polynomial function is also continuous, right? So we can now write f of x as log of 1 plus x plus minus x, right? So this is continuous and this is also continuous. So f of x is a sum of two continuous functions, and we know that if a function is a sum of two or more continuous functions, then the function itself is a continuous function, right? So f of x is continuous in the interval 0 comma x, right? So here we are taking all values of x greater than 0. So here we can assume the interval 0 comma x, right? And here we have the interval a comma b. So this interval, if we compare this interval with this one, then we can easily see that the value of a is 0 and the value of b is x, right? Okay, now let us find out the derivative of f of x. So the derivative of f of x is d by dx of log of 1 plus x minus the derivative of x, right? So the derivative of log 1 plus x is 1 over 1 plus x, and here the derivative of x is 1, right? Okay, now we can simplify it. So we can have here 1 minus 1 minus x divided by 1 plus x. So here 1 and 1 get cancelled. So we are left with minus x over 1 plus x, right? So f prime of x is now equal to minus x over 1 plus x. And we can see that for all x greater than 0, this function f of x is differentiable, right? Or f prime of x exists for all x greater than 0, right? So the two conditions of Lagrange's mean value theorem are satisfied by our function f of x is equal to log of 1 plus x minus x, right? So now the mean value theorem says that there must exist some point x is equal to alpha, where this alpha is it lies between 0 and x, such that f prime of alpha must be equal to f of b minus f of a divided by b minus a. So let us take a is equal to 0 and b is equal to x. So we can now write f of x minus f of 0 divided by x minus 0, right? And here we can easily see that f of 0 is log of 1 plus 0 minus 0. So this is the log of 1, and log of 1 is 0, right? So f of 0 is 0. So we can now have f of x over x, right? So f prime of alpha is equal to f of x over x, and f of x is log of 1 plus x minus x divided by x, right? So now we have this expression. Okay, now see here we have f prime of alpha, right? And f prime of alpha can be obtained from this expression by taking x is equal to alpha, right? So here f prime of alpha can be written as minus alpha over 1 plus alpha, right? So now if we substitute the value of f prime of alpha over here, then we'll get the equation that is minus alpha over 1 plus alpha is equal to a log of 1 plus x minus x divided by x, right? Okay, so now we have this equation, right? And we'll use this equation to arrive at this inequality, right? See here, the left hand side of this equation contains alpha. So we have alpha greater than 0 and less than x, right? So by mean value theorem, alpha should lie between 0 and x, right? So see, here alpha is greater than 0. So 1 plus alpha, if we add both sides 1, we can get 1 plus alpha is greater than 1, right? Now if we take the reciprocal of both the sides, then we'll get 1 over 1 plus alpha is less than 1, right? So the moment we'll take the reciprocal, the direction of the inequality get reversed, right? So alpha is greater than 0, adding 1 to both sides, we'll have 1 plus alpha is greater than 1. Then taking the reciprocal, we'll have 1 over 1 plus alpha is less than 1, right? Okay, now if we multiply both sides by alpha, then what we will get, let us see. So multiply both sides by alpha, because alpha is greater than 0. So there is no harm in multiplying both sides by alpha, right? So we have alpha over 1 plus alpha, and here we have less than alpha, right? Now see, here we have the negative sign. So what we will do, let us multiply both sides by -1, right? So here we are going step by step. So let us multiply both sides by -1. So we have minus alpha over 1 plus alpha, and here we'll have minus alpha, right? And the direction of the inequality get reversed, right? Okay, so now we have this inequality, right? Okay, so now let us once again take this inequality, right? See, here we have alpha is less than x, right? And now if we multiply both sides by -1, we'll get minus alpha is greater than minus x, right? So what we have done here, we have alpha greater than 0 but less than x. So we have taken this inequality, alpha is less than x. We have multiplied both sides by -1. So we have got minus alpha greater than minus x, right? Now this is inequality number 4, right? Okay, now if we merge these two inequalities, right? So if we merge inequality number 3 and 4, then what we will get minus alpha over 1 plus alpha is greater than minus alpha, and minus alpha is greater than minus x, right? So what we have done here, we have merged inequality number 3 and 4, right? Now if we retain these two terms, then we'll have minus alpha over 1 plus alpha is greater than minus x, right? So minus alpha over 1 plus alpha is greater than minus x for all x greater than 0, right? So minus alpha over 1 plus alpha is now equal to log of 1 plus x minus x over x. So here we'll substitute this value, right? So what we will get? We'll get log of 1 plus x minus x over x greater than minus x, right? Now since x is greater than 0, right? So we can safely multiply both sides by x. So we'll have now log of 1 plus x minus x, and here once we multiply both sides by x, we can get rid of this x. So now we have this is greater than minus x square, right? So here x is multiplied with x, so we have x square, right? Now if we take this term to this side, so we have log of 1 plus x, and this is greater than x minus x square, which is our desired inequality, right? So this is how, by making use of the Lagrange's mean value theorem, we have proved this important inequality.